Okay, guys, here we are. Hopefully you are watching this video after having watched the video that says day 13.5, what is a chi-square test? All right, so you either participated virtually, all right, you counted my M&Ms, or you managed to get your own bag of M&Ms and you counted those M&Ms to learn about the mechanics behind what a chi-square test is doing. Today, we are going to talk more about chi-square tests, all right? So we're going to talk about that chi-square goodness of fit test again. I'm going to give you some examples of it using more normal, sorts of data, not counts of M&Ms. And I'm going to show you how to do it in SPSS for those of you guys who are trying to learn SPSS as we do this online. And then I'm also going to introduce to you guys a second chi-square test called a chi-square test of independence that, the mechanics work the same, but it's a slight variation on what's happening there. We're also going to talk about excuse me, we're also going to talk about this table right here which if this were a normal sort of situation, we would draw this table up on the board every day. And I'm going to show you guys how to use this table to determine which of these kinds of tests you need to do. All right, and so when it comes to the data analysis plan assignment, you're going to see some questions like the ones we're working through in the slides today, but they'll be related to your ADHD survey, of course. And you're going to have to tell me in that assignment, based on that question, you should do a chi-square goodness of fit, or based on that question, you need a bivariate correlation. And I'll make a separate video that pulls the assignment up and maybe we'll work through one together and just shows you what exactly needs to be done for that assignment. But I'm going to keep this sheet up here so that it can be our pretend chalkboard, and we will talk about how to use this table and what all the headers and everything mean. While you are working on the data analysis plan, and especially while you're working on the final paper, I want to point out that this document is posted to Blackboard. I believe on Blackboard it's called Table of Appropriate Statistical Tests. On the first page of the document, it gives this table at the top. It also gives the SPSS menu commands for all of the tests that we learn how to do. So, which specific things in the menus do you need to click on to get each of these tests done? And in the second page, it shows you the general hypothesis format for the null and alternative hypothesis for each of these tests. All right, so you would have to, this will make a little more sense after you've watched the next two videos, but you'll have to substitute in your specific numbers here, but this will tell you what should the null and alternative hypothesis look like for each test that you're doing. And then down here at the bottom, this is relevant for when you get to the last lecture about writing up the results. What format should these results be reported in your final paper, right? So I just wanted to show you that that's what's in this document, but we're staying up here with this table of appropriate statistical tests today. All right, so I'm sure some other class that you're in knows how to use Zoom much better than I do. I cannot figure out how to get the PowerPoint slides to be in presentation mode and also allow me to show you other things. So we're just leaving them here in editing mode as we go through this. So that means that there won't be any slide transitions, but hopefully we can all deal with no slide transitions. All right. So in your business stats class, you learn about t-tests. All right. And what t-tests do is they compare differences in means. All right. That's every t-test is going to have something to do with a mean. Is the mean that you observed equal to some specific number? Is the mean for group 1 equal to the mean of group 2? Right? Anytime that you are comparing means, you need a t-test. All right, but in order to use a t-test, you have to have a mean, all right, because t-tests don't do anything else. They just compare means. And that means that you have to have collected data on an interval or ratio response scale in order to do that t-test. Right, because remember that table that we came up with the mean, the median, and the mode, and we said if you have nominal data, you can't calculate a mean, right? But if you have interval or ratio data, you can calculate a mean. That means that t-tests can only be used when the thing that you measured was measured on an interval or a ratio response scale. Right, so this leaves out a whole type of data that we collected, right? Data collected on nominal response scales, that the existing tools that we have available to us do not cover. All right, and so this chi-square test, this new test that we're learning about, covers this case, all right, when the thing that we were interested in measuring was measured on a nominal response scale. So if we have questions about the nature of the responses provided to this nominal response scale, we're going to use chi-square tests, all right, to examine that data. Oh, I'm gonna have to erase this stuff every time, sorry. All right, so the kind of chi-square test that we talked about in the M&Ms video is called a chi-square goodness of fit test. All right, remember in my bad English, I said that what it's asking is, how well does the distribution that you observed in your data fit? How good is the fit between what you observed and some hypothesized or expected distribution? All right, and so in the M&Ms case, we had this expected distribution based on what the Mars website told us should be inside the bag of M&Ms before we open it. And so we wanted to know, is what we observed a good fit for that hypothesized distribution? The hypothesized distribution is something very specific, and we'll see when we do this in SPSS, we actually have to specify exactly what we expect to see for each possible nominal response option. All right, in our examples today, we're going to look at this question. All right, we're going to look at what did our respondents say versus an expectation that 33% of students would be in the Greek system. And oftentimes this is used to look at the distribution in your sample against the distribution in a larger population. All right, so we could look to see, is the distribution of races, all right, this is measured on a nominal response scale, is the distribution of race in Mississippi equal to the distribution of race in the United States? All right, and so remember, this looks like that M&Ms example, except instead of, you know, red, yellow, green, orange, whatever colors are in M&Ms, now we have these race categories. And what the chi-square goodness of fit test is doing is it's saying, are these two numbers similar? Are these two numbers similar? Are these two numbers similar? Etc. all the way across. And then it comes up with one statistic that summarizes the magnitude of the difference between these pairs. All right, and so if these pairs are very different from each other, you're going to get a big chi-square statistic. If these pairs are very similar to each other across the board, then you're going to get a very small chi-square statistic. All right, but the overall question that we're asking is, how good is the fit between what I observed in my sample and some distribution that I expected? All right, let's see how this might show up on the data analysis plan. All right, when we go through these examples in these slides, I'm using this data set. If you want to play along in SPSS, this data set is posted to Blackboard. Under content, SPSS files, it says, it either says something like student data or class examples data. All right, it is not inside of that folder that says class exercise. It's outside of that folder and it just says class examples data. This is from that survey that I referenced in the descriptive statistics video, where I gave the students in my class a survey about where they spend their money and how often they go out for meals. And it also asks them some demographics like what's their gender, how old are they, what year in school. I asked if they're vegetarian, we never use that data. Are they in a relationship? Are they Greek? How often do they work, etc. Okay, so that data is going to show up here. All right, I'm going to show you how to do this stuff in SPSS and how to look at the output. But here's our first question. There was this question on the survey that asked, are you in a sorority or fraternity? All right, and before I even look at the survey data, I know from what the university reported on their website the year that this survey was administered, that 33% of the campus population is involved in the Greek system. All right, and so I can ask this question. The question that might appear on the data analysis plan would be something like 33% of the Ole Miss student body population is in a Greek organization. Are business students, all right, because this sample, you know, we could call them, it's a sample from marketing majors or it's a sample from business students, but we can say, are business students more or less likely than the average Ole Miss student to be in a Greek organization, right? And if we want to, oh, I don't know if it's gonna let me move this now. If we want to, sort of parse out what's happening in this example, this is saying, here is my expected distribution, all right? I would expect, before looking at the data, if business students were just like the average Ole Miss student, then 33% of them should say, yes, I am in a Greek organization, and 67% of them should say no. All right, so before we even look at the data, if business students were just like the average Ole Miss student, oh, did that seriously erase? Then we would expect 33% of them to have answered yes to this question and 67% of them to have answered no, right? It's unlikely that we would see exactly 33% saying yes in our sample and exactly 67% saying no in our sample. And in fact, what we do see is that in the data set, 44% of my students said they're Greek and 56% said that they're not. And so the question is, given that we are seeing these differences between the groups, are these differences pretty small, all right? And we think it's just a fluke of our specific sample, right? We don't think that there's really a difference between our students, our business students, and the general student population, all right? In that case, what we observe is equal to what we expected, all right? Remember, this null hypothesis is not saying what I observed is exactly the same numbers as what I expected. What it's saying is the difference between these two things is so small that it's likely to just be due to chance and sampling error, all right? It's likely just a fluke of our specific sample. I don't think it's telling me, I don't think these differences are telling me anything, signifying anything greater about the population of business students. I just happen to get too many Greek students in my sample, all right? That's one possibility. Another possibility is that this difference is so large that it is unlikely to have been due just to chance or sampling error, all right? And that the differences are so large that I think that they reflect a real population level difference between business students and the general student body. We can see over here are these null and alternative hypotheses, all right? The null hypothesis is always what I observed from my population is equal to what I expected. The alternative is that what I observed is not equal to what I expected, all right? So the null hypothesis, just to sort of go back over what was talked about in the last video, or 2 videos ago when we talked about inferential statistics, the null hypothesis is saying, I see that there are differences, but those differences are pretty small. I think that it's just a fluke of your specific sample. I don't think that it's revealing anything true about the population. The alternative is saying, those are pretty big differences, all right? I think that you are seeing a difference this large because at the population level, business students really are more likely to be in the Greek system than non-business students, or the general student body population. All right, so to find out which one of these hypotheses is more supported by the data, we have to do the chi-square test. All right, let me get rid of all of this writing. I wish it would just erase when I moved on to the next screen, but it does not. All right, so to find out which one of those hypotheses is more supported, we have to do the chi-square test. All right, and the way we do the chi-square test, we go to Analyze. All right, this chi-square test is buried deep down in the menus. All right, the rest of the things, especially the t-test and the descriptive statistics, it's very obvious where in the menus you should be looking, but this chi-square test gets buried. All right, and so if you are working in SPSS, hopefully you'll get used to it by just having to go there so often, but to get there, you go to Analyze, Non-Parametric Tests, Legacy Dialogues, chi-square. All right, in this menu, all right, we haven't done a lot of intro to SPSS type stuff yet, unless you've been watching the videos out of order. So just briefly, in SPSS, when you ask for an analysis to be done, you're going to see a menu that always looks sort of like this. On the left-hand side is going to be a list of all of the variables in our data set, and SPSS is asking us now which variable are we interested in, all right? And so we're gonna move that variable over to the test variable list. Here, we are interested in how many people are in the Greek system. So we're going to move that over to the test variable list. In a chi-square test, we next have to specify what is our expected distribution. All right, SPSS is going to calculate our observed distribution by looking at how people answered this Greek variable. All right, how many ones were there and how many twos, meaning yeses and nos. All right, and we have to tell it what our expected values are. All right, so the default is for all categories to be equal, which in this case would mean that we would expect 50% of students to say yes, they're Greek, and 50% of students to say no, they're not Greek. All right, but that's not what we expect here. Here we expect, as it says over here in the slides, we expect 33% of students to say yes and 67% of students to say no. Importantly here, when you enter expected values in SPSS, you have to list expected frequencies in the same order as the grouping variable, all right? What on earth does that mean? In this data set, 1 equals yes, yes Greek, and 2 equals no, all right, not Greek. This means because 1 is a smaller grouping code than 2, we have to enter the proportion we expect to say yes first, and then the proportion that we expect to say no. If this were coded 0 equals no, and 1 equals yes, then we would have to enter the proportion of no's we expect first, and then the proportion of yeses, because 0 is the smaller coding value than 1. All right, so our data though is coded 1, yes Greek, 2, not Greek. All right, and so we are going to tell SPSS that we expect 33% of people to say yes. You do not enter a percent, you don't enter .33, you just type 33 and click add. And then we expect 67% of people to say no, right? So just type 67 and click add. So now we can see our expected values here. 33% yes, 67% no. All right, and at this point, we just click OK. All right, and SPSS is going to compare this observed distribution against this expected distribution. All right, so here is the result of this chi-square test. Let me show you what's happening in here. This is telling us that 36 people took the survey, 16 of them answered yes, 20 of them answered no. Right, the expected values, SPSS converts that 33 and 67% into counts. All right, so this is saying that 33% of 36 is 11.9 and 67% of 36 is 24.1. All right, so that's just like in the M&Ms example where you took your total sample size of M&Ms, multiplied it by the expected percentages to get your row of expected counts in that table. And then it does all of that other math behind the scenes, and it spits out in this table down here. Here is, let me get my pen. Here is your chi-square statistic. All right, our chi-square statistic is 2.133. Here are our degrees of freedom. Remember, degrees of freedom are equal to number of response options minus 1. All right, so we have 1 degree of freedom here. And here is our p-value. All right. Unfortunately, SPSS never prints out the letter P for some reason. They always print out SIG, meaning significance. When it's a chi-square test, for reasons we won't get into, it's labeled the asymptotic significance. All right, but this is our p-value right here, 0.144. All right, so with a p-value of 0.144, we have to decide if we are going to reject or fail to reject the null hypothesis. All right, remember, if p is less than 0.05, we are going to reject the null. And if p is greater than 0.05, we are going to fail to reject the null. All right, so in this case, our p-value is 0.144. 0.144 is greater than 0.05, so we are going to fail to reject the null hypothesis. All right, and I deleted our null hypothesis on accident, so let's go back to that worksheet. All right, now that we've decided we're going to reject the null hypothesis, we have to get rid of all of this. And If we look at our null hypothesis here, we failed to reject the null, which means that we side in favor of the null hypothesis. Right? We have failed to reject it, which means we are not rejecting it. We're keeping it, which means we are going to conclude that what we observed is equal to what we expected. In this case, what that means is that what we observed is information about business students. Right? Sometimes writing this stuff out for yourself can help you figure out what this means. Right? We observed business students. Our expected distribution was coming from all Ole Miss students. All right, and so what we're concluding here is that business students, what we observed, is equal to what we expected. Business students are equal to Ole Miss students when it comes to Greek membership. All right, so yes, these numbers were not exactly the same, but this test is telling us that the odds of finding this result due only to chance or sampling error, right? And I think it was 0.144. Let's get the output back up. 0.144. This is telling us there is a 14.4% chance that we found this result due only to chance or error. That means if we reject the null hypothesis, there is a 14.4% chance that we're wrong. All right, that if we reject the null hypothesis, we are committing an error, and we're not willing to be wrong that often. All right, how often are we willing to be wrong? Everybody shout it out at home. 5%. All right, remember alpha is set at 0.05. That means we're only willing to tolerate a 5% risk of being wrong when we reject our null hypothesis. This p-value is telling us if we reject the null, there is a 14.4% chance that we're wrong. That's too high. All right, the rent is too high. We're not going to reject the null hypothesis in this case. And so we conclude, while there is some evidence that business students are more likely to be in Greek organizations than the average Ole Miss student, the evidence from our sample is not strong enough to reject that null. And so we conclude any differences we saw here must be due to chance and sampling error. And, you know, in terms of writing this in a final paper, which, you know, we'll get to in its own lecture, but just, you know, for some repetition here, we would just conclude business students at Ole Miss are just as likely as the general student body to be in Greek organizations, hopefully spelled correctly. Right? So this is what we conclude from this test. What we observed is equal to what we expected, and what that means in plain English is that business students at Ole Miss are just as likely as the general student body to be in Greek organizations. All right? One example, done. All right, we're going to do some more examples. Hopefully, as we just do this over and over again, it'll start to make more sense. This is also the situation where I said I'm going to scour YouTube to try to find some videos where other people are teaching in a way that is, you know, maybe clearer than how I'm teaching. So if you're not getting it from my videos, then you can watch the other videos and hopefully get it there as well. All right. Another question on the survey asks students, are you employed at least part-time? All right, so we get this data from students. Oh, I forgot to show you guys how this fits in the table. Well, we'll do it here. Are you employed at least part-time? All right, is this question on the survey. And this survey was given to my students in 2011. And so in 2011, the US Census reported that 72% of undergraduate students in the United States work at least part-time. So we can ask this question, sorry, let me type this so you can see how this would compare to your data analysis plan. Are students at the University of Mississippi just as likely to have part-time jobs as the average US student? All right, so we're asking, is the distribution of responses, all right, is the distribution of yes and no responses that we observed from our sample equal to, all right, is what I observed in my sample equal to some expected value that I got from this outside source. All right, so the 2011 US Census, that's not my survey. All right, this is not data I collected. but they collected some data that I want to compare my numbers to. All right, it's an external reference point. And I want to know, is what I observed equal to this expectation set up by the US Census? All right, when we do this test, we are doing a chi-square goodness of fit. All right, and how this fits in this table. Up here in the table, the first question that you should ask yourself when you're deciding what kind of test needs to be done is you should ask yourself, do I have a predictor variable? And what a predictor variable does is it asks you to to use a question in your survey to divide your sample up into groups. All right, so we're going to see later, you might ask, are the men in my sample equal to the women in my sample with respect to how they answered some other question? All right, and so when you do that, you're dividing your sample up into groups. In that specific case, you would be dividing your sample into groups on the basis of a categorical variable. And so that would mean you would need one of these two tests. With this chi-square goodness of fit test, sometimes this is confusing for people because you say to yourself, well, I am doing a comparison between groups. The key thing here is that these groups are your entire sample, all right? So we're not dividing our sample up. We're just saying everyone in my sample. Is everyone in my sample like some external reference point? All right, and this external reference point is not a variable in our sample that we're using to divide people into groups. It's just a number, all right? Just some number that we're interested in for some reason because it's relevant to our research question. And when we have a situation like that, we don't have a predictor variable, all right? Because the predictor has to come from inside the sample. All right, we have to use data that we collected from our sample to divide that sample into groups. All right, and in this case, this is not coming from inside of our sample. All right, so we have no predictor. And we have no predictor, and the thing that we're interested in is whether or not people have a job, yes or no. This is a categorical variable. All right, remember nominal variables give us categorical data. All right, so we have this categorical outcome that we're interested in. Do people have jobs or not? And when we have no predictor and a categorical outcome variable, we do a chi-square goodness of fit test. All right, so this is how this table gets used, and we'll do this in the table over and over and over again. All right, and especially when we get to that, that practice worksheet video that's SPSS training, but I think it's also just helpful, even if you're not following along in SPSS, it's just helpful to figure out what kind of test you need to do. All right, so back to this question. Are students at Ole Miss just as likely to have part-time jobs as the average US student? All right, where the average US student is defined here as 72% of them having a job in the US Census. All right, so here are the expected values from the US Census. All right, we would expect 72% of students to say yes and 28% of students to say no if Ole Miss students were like the average US population. In the actual survey data, what was observed in my sample is that 50% of students said they worked at least part-time and 50% of students said that they did not, all right? So this question is, are these numbers so different that that difference is unlikely to be due just to chance and error, or are these differences pretty small and I think it's just a fluke of my specific sample? I think that the population that Ole Miss students are just like the average US student. All right, so here's this question down here. Are Ole Miss business majors more or less likely to work at least part-time than the average college student? To get an answer to this, we need to go back to SPSS. We're going to go to Analyze, Non-Parametric Tests, Legacy Dialogues, chi-square. All right, we are no longer interested in whether or not students are in the Greek system. Now we are interested in whether or not they work. All right, so we're going to put the work variable over here. Work is coded 1 equals yes, 2 equals no. All right, so we're going to enter 72%. We expect to say yes if Ole Miss students were like the general population, and 28% to say no. All right, and we just click OK. All right, here's the results of this test. All right, here's our observed 50-50. Here is the 72-28 converted to counts by multiplying 72% of 36 is 25.9, etc. Down here, we have our chi-square statistic is 8.643. The degrees of freedom are 1 again because we had 2 possible response options. And now our p-value is 0.003. All right, and because I cannot keep this written on any sort of board, remember, if P is less than 0.05, we are going to reject the null. And if P is greater than 0.05, we are going to fail to reject the null. All right, in this case, the P value is much smaller than 0.05. All right, and remember, if it helps you with the interpretation of what this means, this p-value is telling us that there is a 0.3% chance, let me write it this way, if we reject the null, there is a 0.3% chance that we are wrong. All right, so there's a 0.3% chance of committing an error if we reject the null hypothesis here. That is within our tolerance of being wrong. So we're willing to be wrong 5% of the time. Here, we're only going to be wrong 0.3% of the time. All right, and so as a result, we are going to reject the null. All right, remember the null hypothesis here is that what we observed equals what we expected. We're going to reject that null. And we are going to side in favor of the alternative hypothesis, which says that what we observed is not equal to what we expected. All right, and so in this case, that means that Ole Miss business majors are not as likely, they do not have the same likelihood of having a job as the general US population. And specifically here, the way that they're different is that Ole Miss business majors are less likely to work at least part-time than the average college student. All right, so if I was writing this up in my paper, I would write business majors at Ole Miss are less likely than the average US college student to work at least part-time. All right, and so the parts of this sentence where I'm getting this from, business majors at Ole Miss, this is referring to the population from which my sample was drawn. So my observed distribution is not equal to, all right, and in this case, it's less than, that's how it's not equal, than the average US college student, that's my expected distribution, to work at least part-time. All right, this is the outcome variable that I was interested in, whether or not they work. All right, so we had this question, are Ole Miss business majors more or less likely to work at least part-time than the average college student? We did the chi-square test. The chi-square test came back and said, based on the data, this is strong evidence to support that Ole Miss students are different than the average US college student. And because of that, we rejected the null. We had strong evidence, we rejected the null, we conclude they're different, right? And this is our conclusion in plain English over here. All right, I can't get a gauge for how you guys feel about this, and unfortunately, I cannot answer any questions that you have, live anyway. All right, but we can do another example, all right, and see if that makes us feel better. All right, so now that all that's erased, let's go on to our next example. This is, if you'll recall in the M&M example, I said that one way in which the chi-square test can be used is to compare the population from which your sample was drawn against some external reference point. All right, that's what we just did in the last two examples. Another way is that you can look, you can ask a question about, was everything, I'm sorry guys, were all possible response options to a question chosen equally often, or did one stand out as being chosen more often than the other? All right, and so this is what we're looking at in this question. All right, so on the survey, students answered this question: at which grocery store do you shop most frequently? They had three options: Kroger, Walmart, Larson's Big Star. No one chose Larson's Big Star, and so because of that, SPSS doesn't even recognize that it was a possible answer because that answer never shows up in the column of data. All right, and so here we're going to ignore that Larson's Big Star was an option and look just at Kroger and Walmart. All right, and so we can ask this question. All right, here's the research question as it might show up on the data analysis plan. Is one grocery store preferred over the other, or are they equally preferred? All right, meaning there are no differences in students' preferences. All right, if they were equally preferred, then we would expect to see a distribution where both stores were chosen 50% of the time. So what this chi-square goodness of fit test is going to do is it's going to say my null hypothesis is that what I observed is equal to what I expected, and what I expected is 50-50. All right, that everything was equally preferred. And the alternative is that they were not equally preferred. All right, so they were not chosen in a 50-50 sort of pattern. One was being chosen the majority of the time, and the other was being chosen, you know, a minority of the time. All right, so remember, when trying to think about how to set up the null and alternative for this specific use of the chi-square test, the null hypothesis is always the test of no differences, all right, that everything's equal. And in this case, that means things are equally preferred. And the alternative is that there are differences, all right? And the alternative is that things are differentially preferred. One's preferred over the other. All right, so in a, you know, in a math sort of way, we're asking, is the distribution I observed significantly different from a null distribution of equal preference? All right, so here is what was observed in the sample. All right, almost 53% of people saying they prefer Kroger, 47% of people saying they prefer Walmart. These numbers are obviously not exactly equal to 50-50. And so the question is, are these differences large enough to be unlikely to be due just to chance and error? In other words, are these differences large enough that we think they're reflecting a true population level preference for Kroger over Walmart? Or are these differences small enough that I think it's just sampling error? It's just a fluke of the specific people in my sample. And if I had gotten a different group of people, I wouldn't expect to see the same result again. To find out, we have to go back to SPSS. Let's erase all of this. All right, so we're going to go back to SPSS. And we're going to do another chi-square goodness of fit test. All right, non-parametric tests, legacy dialogues, chi-square. We are no longer interested in if people work. We are interested in this store frequency variable. All right, it asks which store do you shop at most frequently. That's why it's called store frequency. And here we are interested in expected values where all categories are equal. All right, so we want to test, did people choose these two options equally, all right, at a 50-50 rate, or did they choose them at some other rate? All right, and we click OK. All right, here are the results down here. Let me get my pen back. All right, so here's what we observed. All right, that's that, you know, it wasn't exactly 50-50, it was 53-47 is coming from this 19 and 17. Here's the expected 50-50 distribution. All right, hopefully at some point you guys can start to get a feel for this. These are probably not going to be significantly different because while it's not exactly the same number, it's pretty close to being the same number. And we see down here, because those numbers are so similar, we end up with a very small chi-square statistic. And with a very small chi-square statistic, we get a very large p-value. All right, this p-value is telling us, again, just as a reminder, if we reject the null and conclude that Kroger is preferred over Walmart. All right, so if we draw this inference at the population level, I think that Kroger is preferred over Walmart. Based on this evidence from my sample, there is a 73.9% chance that the inference is wrong. All right, so if we took this evidence and said, well, 53 is bigger than 50, all right, and so I'm going to conclude that business students or students at Ole Miss, whatever we want to say, this population that our sample represents, that these students really do prefer Kroger over Walmart, there's a 74% chance that that inference is wrong, all right, and we're only willing to be wrong 5% of the time, all right, so P is greater . All right, so our p-value is much greater than 0.05, so we are going to fail to reject the null hypothesis. Remember, the null hypothesis here is equal preference. All right, so we're failing to reject that, which means we're concluding that that is what is more supported. All right, and so we're going to say that we fail to reject the null. We conclude that Ole Miss business students prefer Kroger and Walmart equally. All right, so there's no difference in preference for one of these stores over the other. They are equally preferred. All right, roughly half of students like Kroger and roughly half of students go to Walmart most frequently. All right, and that's what we have learned from this test. Yes, we saw this small difference between our sample and a 50-50 expected distribution, but that difference is so small that we think it's just a fluke of our sample. We do not think it's representing some real population level difference in preferences. All right, that's what we've learned from this test. Let's get rid of all the scribbles. All right, I believe that's our last chi-square, and we're gonna move, we're gonna move now to the test for independence. All right, so let me pull up the table. So many screens open. All right, we have a second kind of chi-square test. It's called a chi-square test for independence. What the chi-square test for independence does is it asks, if we set up a crosstab table, all right, like this one right here, right? Remember, the crosstab takes two variables and it looks at the count information for those two variables in conjunction. So if we divide up our sample based on how they answered this male-female question, so we have two groups now, males and females. How did the males answer this Kroger versus Walmart question, and how did the females answer this Kroger versus Walmart question? We have this crosstab table now, and what the chi-square test of independence asks is, instead of looking at observed versus expected, it asks, is what we observed for group 1 equal to what we observed for group 2? All right, so the math is basically the same. All right, there's some behind the scenes stuff that differs that we're not going to get into, but the math for all intents and purposes is the same. We can think of this as our observed distribution and this is our expected distribution, except we observed both of these. All right, both of these are coming from within our sample, and the way we get two groups to look at is that we use some variable that was measured on our survey to divide our sample into groups. That is a predictor. All right, so on our survey, we asked people, what's your gender? Everyone answered male or female. If we use their answer to that categorical measure on our survey to divide them up into groups, and then ask, did these two groups answer this nominal question in the same way? Then we have a categorical predictor and a categorical outcome. All right, which store do you prefer, Walmart or Kroger? That's a categorical outcome. And so we are going to do a chi-square test of independence. All right, categorical predictor, we're using the data from a question on our survey, a nominal question on our survey, to divide our sample up into two groups. All right, this predictor on the survey is going to tend to be things in real life, but also on your data analysis plan, like, are you in a Greek organization? Yes or no? What's your gender, male or female? What's your race? All right, you can have more than two categories. So race would have multiple categories. What's your year in school? All right, 4 or 5 categories there. All right, so you have, it's typically, you have some variable that divides people into kinds of people, all right, male kind versus female kind of person. And then you want to know if those two kinds of people answered some other question in the same way. So in this case, are these two kinds of people the same when it comes to where they grocery shop, or are they different? All right, so we're looking at this question, is there a relationship between gender and store preference? All right, so when I divide my sample into two groups based on their gender, do I see those two genders indicating the same store preference or different store preferences? All right, and so in our table, we see that the men's answers are not exactly equal to the women's answers. All right, so the men's answers in our sample, and of course this is a very small sample, but you know, a little bit more of the men say Walmart and a little bit more of the women say Kroger. So it seems possible that there's a difference here, all right, that women prefer Kroger and men prefer Walmart. And so given that I've recognized these differences in my sample, the question is, are the differences I observed in grocery store preference across gender more likely to be due to chance and randomness? All right, it's just sampling error. All right, that's our null hypothesis. Yes, I see a difference. I think that difference is just error. Or are the differences so large that we think they reflect an underlying population level gender difference in grocery store preferences? All right, that's our alternative hypothesis. These two groups are not the same. at the population level when it comes to where they prefer to grocery shop. To find out which one of these two is more supported by the data from this specific sample, we have to do the chi-square test of independence. Scribble, scribble, scribble. You guys are real troopers at home. I can only imagine how painful it is to watch me scribble on these screens. Okay. In SPSS, to get this test, because this test is built off of a crosstab table, all right, we're going to start in the descriptive statistics box so that we can get that crosstab table. All right, so we're going to go to Analyze, Descriptive Statistics, Crosstabs. Okay, technically here, it does not matter which variable you put in the rows box and which variable you put in the columns box, but I recommend putting your predictor variable in the columns box. All right, remember how our table was set up. No, draw. Male, female, Kroger, Walmart. All right, that's how we have the table set up in the slides. This is generally how crosstabs get set up, where you put the predictor variable at the top and then the possible answers that they could have given over here on the left. So we're going to set this crosstab up the same way. We're going to put gender into the columns box. That means it's going to be the column header. All the different gender answers will be in different columns. And then we're going to put that store frequency variable into the rows box, right? Because it's the row headers. All right, at this point, if we just clicked OK, SPSS would just spit out the crosstab table. All right, so it wouldn't give us any chi-square statistic. It would just say, here are the frequency counts, how many people answered this question in each of these groups, male versus female. If we want the chi-square test, we have to click where it says statistics over here on the right. All right, maybe I did that too fast. Over here on the right where it says statistics, click that box, and then check the box that says chi-square. All right, so that means it's going to come up with the crosstab table, but then it's also going to do this chi-square test of independence to tell us if the men's answers are different from the women's answers. All right, and now we click OK. All right, so our output here looks a little different than what we saw previously. All right, here we have the crosstab table. All right, so this is what we saw in the PowerPoint slides. All right, 8 men said Kroger, 9 men said Walmart, 11 women said Kroger, 8 women said Walmart. What we need to know is, are these differences large enough that they're unlikely to be due to chance and sampling error? Ignore everything down here except for the first row where it says Pearson chi-square. Right, remember we did a chi-square test, right? And so we're looking for a chi-square statistic. Here is our chi-square statistic. We have 1 degree of freedom because the men and women could choose between 2 stores, so 2 minus 1 is 1. And here is our p-value. All right, I miss standing in front of class and saying to you guys, if p is 0.516, do we reject or fail to reject the null hypothesis? And at this point, there would be slightly more confident murmurs that we are going to fail to reject. All right, and because we fail to reject, that means we accept the null hypothesis. Let me get rid of this stuff. Remember, p-value 0.516. We're going to fail to reject the null hypothesis. With a chi-square test of independence, our null hypothesis is that group 1, all right, in this case, men, are equal to women, and the alternative is that, men are not equal to women, right? And in this case, with a p-value of 0.516, we are going to fail to reject, which means we side with the null hypothesis, and we conclude that men equal women. All right, so if we wanted to write out what is our conclusion in plain English, right, and this is what you guys are going to have to do when you write the final paper, right, I would write something like men, let's see, what would I write? There is no difference between men and women in terms of their grocery store preferences. All right, so there's no difference. Men and women are the same. All right, importantly here, this test is asking, is group 1's pattern of answers equal to group 2's pattern of answers? It does not ask, do they like Kroger or Walmart better? All right, so we can't make a conclusion like everybody likes Kroger or everybody likes Walmart. Instead, we can just conclude that whatever group one's answers are, it's the same as whatever group two's answers are. When we conclude that there is a difference, then we look into the actual pattern of responses to see what that difference is. Okay, so our first example of a chi-square test of independence. Hopefully we feel okay about this one. Let's move on to another example. All right, we ask on the survey, are you Greek? Yes or no? We ask on the survey, do you have a job? Yes or no? All right, and so we can ask, are Greek students more or less likely to work than non-Greek students? All right, so we have our null hypothesis, Greek students equal non-Greek students, all right? Our null hypothesis is always group one equals group two, all right? These two kinds of students are the same with respect to how they answered this question. Our alternative is always if the two groups are not the same, all right? Greek does not equal non-Greek, all right? These two groups are different from each other. All right, so when we look at the data that was provided by the sample, among the Greek students, 5 had a job, 11 did not. Among the non-Greek students, 13 had a job, 7 did not. All right, we're starting here to see, what appears to be a larger difference. All right, so the chi-square test is going to ask, are these two numbers the same? And are these two numbers the same? All right, and so it looks like there are some differences. And so the question is, are the differences that we observed in the sample more likely to be due to chance and sampling error? All right, again, I think this is a fluke of my sample. I think at the population level that these two groups are the same. I just happened to get a sample that revealed some differences. Or these groups are not the same. At the population level, Greek students are less likely to work, and that's why I'm seeing this in my sample, all right? So the truth at the population level is just showing up in my sample, and that's why I see these differences, all right? And that corresponds to our null and alternative hypothesis. And in order to learn which one of these is more supported, we have to go to SPSS and do the analysis, all right? So we go to Analyze, Descriptive Statistics, crosstabs. All right, our predictor variable now is not gender. It is whether or not students are in Greek organizations. And our outcome variable is not where they go grocery shopping, but the thing that we're interested in that these Greek and non-Greek students are doing is whether or not they work. All right, and this will already be checked, but we can just click statistics to double check that that chi-square box is checked. Press continue and okay. All right, and so here we see the data that's still up over here in the PowerPoint slides. 5 Greek students said yes, 11 said no, 13 non-Greek students said yes, 7 non-Greek students said no. And the question is, how strong is this evidence? We look at this top row. We have a chi-square statistic of 4.05 and a p-value of 0.044. All right, with a p-value of 0.044, do we reject or fail to reject the null hypothesis? I feel like if we were in class, this would just be left up on the board somewhere. If p is less than 0.05, we are going to reject the null. If p is greater than 0.05, we are going to fail to reject the null. We'll see if we can just leave that up there. All right, so with a p-value of 0.044, that p-value is less than 0.05, so we're going to reject the null. All right, that means this is strong enough evidence to reject the null. All right, so we are going to reject this possibility, and we're going to conclude that this result represents a real population level difference, and that difference specifically is that Greek and non-Greek students are different, all right, regarding how they answer this question. All right, and so if we were writing this up in our paper, we might say something like, Greek and non-Greek students are not equally likely to have part-time jobs. The evidence suggests that Greek students are less likely than non-Greek students to work at least part-time. All right, so we're saying our alternative hypothesis was that these two groups are different. All right, what that means is we're making this inference that yes, the sample suggested they were different, and the statistics suggest that we saw this difference in our sample because there is an underlying population level difference. All right, and so we conclude Greek and non-Greek students, all right, importantly, not just the ones in our sample, but all the students at Ole Miss. Greek and non-Greek students on average are not equally likely to have part-time jobs, and the evidence suggests that Greek students are less likely than non-Greek students to work at least part-time. All right, so that's what the result of this test is telling us. There's a difference between these two groups, and then we use the number inside the tables to interpret that difference. All right, how are they different? Okay, I think we have one more example. Then you can go back to Netflix. All right, let me erase all this over here too. Okay, last example. We're going to leave that p-value stuff up there at the top. This example, I want to show you, we're going to sort of segue into t-test, which is the next video, but I want to show you how important it is to do the highest level analysis possible on your data. All right, so if you will recall, when we talked about, so we had mode, median, and mean, and we had nominal, interval, and ratio data, and we said that when you have nominal data, you can only report the mode, all right, or frequency data, how many people answered in each way and which way was the most popular. And with interval and ratio, you can calculate the mean. But when you have interval and ratio data, you can also report frequency information. Nothing's stopping you. It's not inappropriate to report that frequency information. You just have more advanced analyses available to you. But because we can report information about frequencies, if you have interval or ratio data, you could do a chi-square test if you wanted. All right, so we have this question, do Greek students eat dinner out more often than non-Greek students? All right, so here's our predictor variable, Greek versus non-Greek. We have this outcome variable, which is the number of nights per week that students are eating dinner away from home. Here are all of the possible options that they could have circled, 0 through 7. And here is the frequency data. All right, so here's how many Greek students circled 0, how many Greek students circled 1, etc. And the same for non-Greek students. Now, when we set this table up like this, it's a crosstab table. And so we can do a chi-square test of independence to ask, is this distribution of responses equal to this distribution of responses? All right, so is the pattern of answers for Greek students equal to the pattern of answers for non-Greek students? All right, and our null hypothesis would be that Greek students are equal to non-Greek students, and the alternative hypothesis would be that they are different. All right, so one of these two things is more supported by our data, and the question is which one? All right, that these two things are the same or these two things are different. When it's kind of hard to get a feeling for what the answer should be by looking at this table. So instead of looking at this table, we can put this as a clustered bar chart. All right, and so the blue bars are the frequency count. All right, so here's the y-axis represents how many people answered each of these possible answers that's on the x-axis. Blue represents the non-Greek students, red represents the Greek students. And we can sort of get a feeling here that this data suggests that the Greek students may be going out for dinner more often because all of these red bars are sort of clustered over on the right-hand side of the table, whereas the blue bars have sort of more of a normal distribution. There's a lot of answers in the middle, fewer answers at the extreme ends, and all the Greek students' answers are pushed over to the right. So it sort of suggests that maybe Greek students are more likely to be going out than non-Greek students. To get an answer to this question, all right, are these groups going out the same amount or are they going out at different rates? We could do a chi-square test. If we did that chi-square test, I'm not going to pull it up in SPSS, but if we did that chi-square test, here are the results. All right, chi-square statistic 13.345, p-value 0.064. With a p-value of 0.064, would we reject or fail to reject the null hypothesis? All right, looking up here, we would fail to reject. And that means that from this chi-square test, we would conclude that Greek and non-Greek students go out for dinner at the same rate. All right, so they're going out for dinner the same amount of nights per week. However, there's another way that we can analyze this data. All right, remember the chi-square test analyzes counts and frequencies. All right, so it's comparing the counts in those two columns, but number of dinners is ratio level data, which means that we can calculate the mean. All right, and as I said in the very beginning of this slide, comparing means is the domain of t-tests. All right, so as we're going to learn about in the next video, you could do a t-test here to ask, is the mean for Greek students equal to the mean number of nights out for non-Greek students? All right, so instead of looking at the counts, how many people said 0, how many said 1, how many said 2, you can take the average. What is the average number of nights that Greek students said? What is the average number of nights that non-Greek students said? And ask if those two averages are equal to each other. This is a independent samples t-test. We will learn about it in the next video. When you do this test, for some reason I don't write down what the t-statistic is, but the p-value is 0.034. With a p-value of 0.034, we would reject the null. All right, and in plain English, we would conclude, because the mean for Greek students is higher than the mean for non-Greek students, all right? Greek students were going out on average 4.5 nights a week. Non-Greek students were going out on average 3.2 nights a week. We would conclude that Greek students go out for dinner more often than non-Greek students. All right, so same exact data set. All right, same exact data set, two different tests. One test is concluding that Greek and non-Greek students go out for dinner at the same rate. The other test is concluding Greek students go out for dinner more often than non-Greek students. All right, when this example highlights, t-tests are more powerful than chi-square tests when you have interval or ratio data. All right, so when you have continuous data, if there is a difference between groups, the t-test is more likely to identify it than the chi-square test. All right, and so if you have interval or ratio data, while it is possible to do a chi-square test to look at that data, it is more appropriate to do a t-test. All right, the t-test is going to be more powerful, more able to detect differences if in fact they exist. All right, and so in the next video, we are going to look at t-tests. All right, examples when we want to compare means. All right, so this is all I have about chi-square tests. As I mentioned before, I'm going to try to find on YouTube somebody else, maybe like a Khan Academy video, maybe that would be good, talking about chi-square tests. And sometimes they might talk about things in more detail than we need. So I'm going to try to find one that's sort of on our level, but I will post that to the YouTube channel. Additionally, please, when you are studying these tests and trying to figure out, especially when you're doing the data analysis plan, which test you need, use that SPSS study guide that's on Blackboard, because it shows you not only screenshots about how to do it in SPSS, but it also talks sort of conversationally about why you need a chi-square test in this specific instance and how to interpret the results of that chi-square test. All right, so there are several different options available to you. Please take advantage of them. Please, if you have questions, to be honest, I don't know the best way to get the answers conveyed. Leave comments on the YouTube videos, and YouTube notifies me that there are comments, and I will come back and answer questions that are in the comments. Send me an email with your questions, and I will, remove your name, but forward the class your question and my answer to it. I'm thinking about setting up a Google Doc that we're all on, where people can just ask questions and I can go back and update the Google Doc with answers to the questions. If you feel like you need office hours, all right, where you're working on the data analysis plan and you are just unable to figure out what's going on, then email me and we can set up a time to use Zoom, or the university tells us there's something called Google Meetup. I don't know how to use that yet, but I'll figure out how to use it, and then we can have some face-to-face meeting that way to try to help you with this data analysis plan assignment. Okay, wash your hands. I'll see you guys next time.